In the last lecture, we talked about energy, and particularly radiation, and its different wavelengths. In this lecture, we're going to talk about the energy balance of the Earth. The energy balance of the climate system, how different gases affect the radiation that comes from the sun and the radiation that comes from the Earth. So what we're going to do in today's lecture is go through this energy balance for the Earth system, and in particular the role that different gases in the atmosphere, the so-called greenhouse gases, how they affect radiation, and the other gases in the atmosphere. What's the difference between greenhouse gases and the other gases? So what we talked about in the last lecture was that the radiation from the sun is short wavelengths, visible radiation. That comes from a very hot object. The surface of the sun's about 5,000 Kelvin. And also infrared radiation, or long wavelength radiation. Long wavelengths here, short wavelengths all the way over here. The Earth is a much cooler temperature, has infrared radiation, and we can't see it. So what about these different ideas? Well, we know that that short wavelength radiation from the sun is going to be absorbed by the Earth's surface. Some of it will be in fact reflected, but in terms of energy balance, about 70% of the sunlight received at the surface of the Earth is going to be absorbed either at the surface or the atmosphere. That absorbed radiation heats up the surface of the Earth. And once the Earth's been heated up, it will re-radiate energy. And the amount of radiation that's emitted from the surface of the Earth depends upon its temperature. Now, if there was no atmosphere in the Earth at all, then there'd be a balance between the incoming sunlight and the heat radiation that would come up from the surface, and there wouldn't be anything to absorb that heat radiation. Eventually, the incoming sunlight and the outgoing heat radiation would come into balance. That balance would lead to an average temperature of the surface of the Earth of around minus 15 degrees Celsius. And that means the Earth would be too cold for most life on Earth. In fact, the Earth would essentially be covered by snow and ice. Now, we don't have that. We know the average temperature is a lot hotter than minus 15 degrees Celsius. We know that, in fact, the surface of the Earth isn't primarily covered by snow and ice. Something's going on. And that thing that's going on is that there are certain gases in the atmosphere that we call greenhouse gases that absorb some of this infrared radiation or heat radiation. These gases that absorb the heat radiation emit some of that radiation back down to the surface, and some of it's emitted out to the space as well. And as we then increase the greenhouse gas concentrations in the atmosphere, then we would expect the Earth's temperature to warm up. Now, this issue of how the concentrations of greenhouse gases affect the Earth's temperature, and in fact, what greenhouse gases are, was not discovered a few years ago. It was actually understood by scientists in the 1800s. And if we look at the different roles of greenhouse gases in the atmosphere and how this energy system works, we can see it on this slide. And I'm going to move across a little bit more so that you can see it. Well, the first thing is that sunlight from the sun warms up the system. Not all of it is absorbed. Some of it is radiated or reflected by the surface of the Earth. So 70% of the sunlight coming in from the sun is heating up the Earth's surface, and the atmosphere, 70% is absorbed. That then heats up the atmosphere and the surface of the Earth, and that then loses energy, first of all by infrared radiation from the surface of the Earth here, as well as losing heat by direct warming up the atmosphere above it through conduction, and also transfer of heat by thermals and evaporation. So evaporation is the transfer of energy through converting liquid water into water vapor, and then the water vapor being transferred away from the surface. But the dominant way that energy is lost from the surface of the Earth is through infrared radiation. Now, that infrared radiation or heat radiation is absorbed by clouds and also absorbed by the atmosphere. And then the clouds and the atmosphere re-emit some of that radiation downwards. That balance at the surface of the Earth between the absorbed sunlight over here and the heat radiation here leads to an extra source of energy, the infrared radiation coming downward, and that's what means that the energy, the temperature of the climate system, averaged across the whole surface of the Earth, is around 15 degrees Celsius. 30 degrees warmer than if the Earth had no atmosphere and no greenhouse gases. That's what we call by the greenhouse effect. But actually what we're concerned about is not that greenhouse effect, but what happens when we add more greenhouse gases to the atmosphere. Now, in this basic greenhouse effect, the most important greenhouse gas in the atmosphere is water vapor, because that has the highest concentration in the atmosphere. That's the most important greenhouse effect. But actually, water vapor is determined by the temperature of the atmosphere. It's cycled around in the water cycle. It's evaporated from oceans and it rains out, on the typical lifetime for water added to the atmosphere is that it rains out within a week. Whereas if we add carbon dioxide, it's what's called a long-lived greenhouse gas. It's cycled around between the atmosphere and the land surface, or the atmosphere and the ocean, and isn't long-term removed for 100 or 1,000 years or even longer. So we call carbon dioxide a long-lived greenhouse gas, and the possible effect of carbon dioxide in the atmosphere was determined more than 100 years ago. Let's look at the relative importance of sunlight from the sun and heat radiation from the atmosphere in warming up the surface. Remember, the fundamental energy source is sunlight from the sun, but actually in the surface temperature, the energy from the infrared radiation is around 320 watts per square meter, whereas the energy from the sun is only about half as much, 168 watts per square meter. So actually, energy from the atmosphere radiated downwards is the dominant source of heat at the surface. We know that because we cool down at night, but we don't cool down to absolute zero. There is still an energy source from the atmosphere. We also know that when there's more greenhouse gases, more clouds, more water vapor, the atmosphere doesn't cool down as much. There's plenty of evidence supporting the relationships, the energy balance, and our understanding of the energy balance is well known. Well, now what happens if we add more carbon dioxide to the climate system? Well, if we instantaneously add more carbon dioxide to the climate system, then that absorbs more of the outgoing heat radiation, less goes out to space. And then there's an imbalance. And the imbalance is such that the temperature of the surface of the Earth, because less heat radiation is being lost, same amount of sunlight is coming in, climate system warms. Another way to think about it is as shown on this graph here. The black line here is the typical temperature, and temperature decreases with height in the atmosphere. So what that means is temperature decreases with height in the atmosphere. As we add more carbon dioxide really makes the atmosphere opaque. For the same amount of energy to be lost from the atmosphere, in other words, the same amount of energy to be lost from heat radiation, we need to be at the same point in terms of temperature here. For that to happen, adding more carbon dioxide means that the level of warming, or the temperature, the Earth's surface warms up down here, the temperature cools off with height as we go up here, and actually we've ended up with the same amount of energy lost from space, and the greenhouse gases have made the atmosphere more opaque. So there's two different ways to think about the greenhouse effect. One way is to think of it like a blanket. Adding more carbon dioxide means that there's less energy going out to space for a short period. That less energy means that less energy going out means the sunlight is warming up the climate system and you end up with a warmer temperature. But eventually we come into an equilibrium. A warmer temperature at the surface means that there's warmer temperatures all through the atmosphere, and the same amount of energy is coming from a higher level in the atmosphere out to space because there's more greenhouse gases causing more absorption in the atmosphere. Yes, it's complicated, but it's actually a well understood process, and that well understood process is determined by different greenhouse gases in the atmosphere. And the critical gases in the atmosphere, we know the dominant greenhouse gases in the atmosphere are oxygen and nitrogen. These gases with just 2 atoms in a molecule. But the greenhouse gases, the ones that we talk about, the most important greenhouse gas over here is water vapor, H2O, 3 atoms in a molecule. There are other greenhouse gases like carbon dioxide, 3 atoms. Methane, 5 atoms in that molecule. Any gas which has 3 or more atoms in it will be a greenhouse gas and will absorb infrared radiation. So what we're interested in is, as greenhouse gases, the ones that have long lifetimes in the atmosphere and that are going to stay around in the atmosphere long enough. So, as I said before, water vapor only has a lifetime of a week, whereas carbon dioxide has a lifetime between 100 and 1,000 years. Methane has a lifetime of 15 years. Nitrous oxide has a lifetime of about 100 years. Those are the gases we're concerned about. It's not new science. Arrhenius published a paper, 1896, that talked about increasing carbon dioxide concentrations in the atmosphere associated with burning coal. And he made a prediction that if we doubled carbon dioxide concentrations, temperatures would rise around 5 to 6 degrees. That's probably too much, but it's still a possibility. But he said that that doubling of carbon dioxide concentrations from burning coal would take 3,000 years. Unfortunately, he underestimated the time that it would take for humans to dig up enough coal and burn it, because he underestimated the efficiencies of modern technologies, digging up coal, digging up oil, and burning it. So we have nearly, but not completely, doubled carbon dioxide concentrations in the atmosphere, and the most likely time for that to happen is probably around 40 years. We've already added 100 parts per million of carbon dioxide to the atmosphere. We only need to add about another 150 parts per million, 160 parts per million to double the concentration. And we've already added 100. So, sometime this century, we will have doubled the carbon dioxide concentration. We'll look at those consequences when we talk about climate change in future projections later on. So, to summarize, the greenhouse effect is due to changes in the energy balance of the climate system. Greenhouse effect is critically important because there are gases in the atmosphere called greenhouse gases, triatomic molecules or molecules with more than that absorb heat radiation and affect the energy loss to space. This is not new science. It's been known about. The role of infrared absorbing gases and the possible role of increasing carbon dioxide has been known about for more than 120 years. It's not new science. It's actually tried and tested science. And we're going to learn more about that science in the next lecture.